Hello, everyone. We're a team from TDK Ventures. My name is Catherine. I'm working for TDK Ventures deploying our fund EX1. EX means energy transformation. So we're looking at all the investment opportunities in decarbonization and electrification. And Josh and Anko, you want to introduce yourself as well?
Yeah. Hi, everyone. My name is Ankur. I'm an investment director at TDK Ventures, and I cover AI, compute, and connectivity investments out of our third fund. Nice to meet all of you, and I look forward to sharing our thoughts here.
Great. All right. Thank you both. And thanks to everyone for joining. My name's Josh Rubnitz. I'm an investor with our climate fund, Fund EX1, focused on early stage seed, Series A, Series B startups innovating in future decarbonization and the energy transformation. And I think before we dive in, I want to say a huge thank you to SOSV for having a great event and inviting us to be part of the Climate Summit. And we appreciate you all for joining TDK Ventures as we take you through the journey of an electron and areas that we're following of innovation in an energy landscape that is being defined by growth in data centers. So, for many of us, it may be surprising to learn that the US has actually been stagnant in terms of our energy growth for about 20 years. This dates back to 2005, maybe even earlier, which makes current and future increase in electricity demand really unprecedented. This demand growth is definitely driven largely by AI, which we have to nod our head to, but it's also a focus on reshoring manufacturing and electrification in general that's causing electricity to spike. This really unprecedented blue ocean growth is leaving consumers feel fearful of the future, and rightfully so. Some regions are seeing energy prices increase already. And TDK Ventures believes that to solve this challenge, we require innovation at all stages of the journey of an electron. Startups are pioneering solutions in all stages of this journey, which we will travel and maybe have a little bit of back and forth amongst our team today. Innovation is happening early on in how electricity is created, later down the value chain, where it is transmitted, stored, delivered, and ultimately how power procurement may look for large loads like data centers. Finally, we're also seeing innovation in how power is consumed, or very specifically, how compute may happen. Before we begin the journey, let's go over a little bit of background on TDK Ventures. So, at TDK Ventures, we've been investing in hard tech startups since our inception in 2019. We've backed nearly 50 of the most innovative hard tech companies spanning computing, mobility, industrials, clean tech, and next generation materials. We're proud to have recently launched our first fund focused entirely on the energy transition. We call it Fund EX1, and it's a thematic fund focused on EX. We've also recently unveiled Fund 3, which is a more broad, general deep tech fund kicking off in 2025. It's a very busy time for TDK Ventures. So, when you interact with TDK Ventures, you'll notice that we have a very strict code of conduct that defines the way you'll interface with us. Firstly, we invest with purpose in solutions that are empowering entrepreneurs to contribute to society. We always try to raise the bar for ourselves and our ecosystem to collaborate as one team reaching for the sky. Importantly, we always generate intelligence that delivers deep insights for TDK as well as our co investors and the deep tech community at large. And then, admittedly, we as a team have a slight bias towards entrepreneurs first. Entrepreneurs are the true drivers of the innovation story, and we see our job at TDK Ventures to scale the impact of entrepreneurs by providing them timely support in areas that have a real impact for them. Our commitment to supporting these entrepreneurs is reflected by our incredible portfolio that spans innovation across digital transformation and the energy transformation, and many parts that touch on the journey of an electron. We're honored to support companies innovating across the energy transformation in sectors like hydrogen, battery manufacturing, home electrification, and more through the digital transformation side, including portfolio companies innovating in humanoid robotics, high speed networks, and AI accelerator hardware. Okay, we will now dive into part one of the journey and discuss innovation in the creation of electricity. Energy generation has undergone several major transitions, that is, energy transitions. Historically, these have been fairly manageable shifts from wood to oil to coal to natural gas. But right now, we are undergoing the largest step of all. The current focus is on transitioning away from these hydrocarbons that are decoupled, 24/7 firm sources of energy to low carbon methods of generation, which are largely intermittent renewables. Low carbon generation methods like solar are already cheaper, quicker to build, and better for the environment today, though, of course, as mentioned, they face intermittency challenges. We're also seeing a lot of novel low carbon generation methods like nuclear fusion and next generation geothermal that show tremendous promise, especially for baseload energy needs that may appear a little bit more like the traditional hydrocarbon load topology of the past. And this topology is really where we've built our grid to agree with historically. Our existing energy system is built around these 24/7 oil and gas energy sources. There's very high inertia and high cost to move away from this infrastructure. Wind and solar, as mentioned, are attractive new sources of generation, and they're already in mass deployment. However, they are intermittent and lead to grid constraints like long interconnection queues and instability. They can cause blackouts and high prices due to the relatively foreign nature of these intermittent resources. Hydropower is also mass adopted, but is both location and resource constrained. We're tracking more novel forms of energy production in the US, like small modular reactors, nuclear fusion, and next generation geothermal. Some notes on these technologies: small modular reactors have faced some operational challenges, but are seeing increasing resource backing both from private support and public policy very recently. Fusion, nuclear fusion that is, could be a holy grail. It produces minimal nuclear waste and no possibility of nuclear runaway, though we do see that it will require some years and large amounts of capital to commercialize. Next gen geothermal technologies have high theoretical promise across the board. However, the conventional business model of subsurface technology has barred scale development. It's a very binary risk in exploration and long payback periods. I'll hand it over to Catherine to introduce our nuclear fusion company, Type 1 Energy.
Sorry, just realized I'm on mute. Just unmuted myself. Yeah, so thanks, Josh. As Josh shared, we have several portfolio companies that we already invested in the base 24/7 base clean load sector. So one of them is called Type 1 Energy, which is a nuclear fusion innovator. They adopt a stellarator approach, which is a magnetic confinement fusion. They use the shape fields for steady state plasma rather than the classic tokamak reactor. So fusion remains a holy grail of zero carbon baseload power with very high energy density and low fuel input. If successfully commercialized, this could shift the economics of grid baseload very significantly. Another company that we invested in is called Rotherm. So Rotherm is a advanced geothermal technology. They're building a next generation geothermal system that is optimized to be commercial scale today, and instead of after years of development and hundreds of millions of dollars of investment. So geothermal also we view it as a long appealed as long baseload clean power, but has been limited by site specificity, high drilling and exploration risk, water issues, and a lot of geology constraints. What Rotherm doing differently is that they developed this fully cased, pressurized closed loop system that uses a novel working fluid, which could achieve 50% higher efficiency compared with water-based binary cycles. And thus, it can deliver much lower operating and also maintenance costs that we believe could dramatically change the unit economics and able to scale and unlock massive resources spaces.
Catherine, nuclear and geothermal are clearly very clean and appealing sources of energy. When do you think they will achieve fossil fuel pricing? And when do you think they will reach significant share of the grid mix?
Our understanding is nuclear and geothermal, they're not going to completely replace fossil fuels by 2030, but both can already become pretty cost competitive with fossil fuel baseload in the favorable markets. For nuclear, our understanding might be later, probably between 2035 to 2045, with a meaningful market share to capture about 15 to 25% in the some markets. For geothermal, we're actually already seeing some of the levelized cost of electricity for from EGS or AGS lower than $100 per megawatt hour now, and very soon to achieve about $45 per megawatt hour by 2030. And we expect they will get a meaningful market share, about 5 to 10% in many markets around 2030.
Great. Thank you.
And actually, I'm going to continue to share our presentation to talk more about the next step when the electrons, after the electrons generated from this clean base load and how it's delivered to the data centers and how it's stored during the transmission. As you can see right now, we have a very interesting problem in our power grid. On one side, if you see the graph on the right, upper right, you will see this is all the queue lines waiting to be interconnected for those new energy generation projects, solar and wind. Unfortunately, every year there's terawatt hour of renewables being curtailed because they cannot be integrated to the grid. Ironically, on the other side, on the demand side, all the data centers, hyperscalers, tech giants, they're crying for access to power because I just saw a news recently. Microsoft, they purchased a lot of NVIDIA chips, but they're just sitting there doing nothing because to build a new data center to accommodate these GPUs, the time may take for up to 10 years to just get interconnect. So the big problem is on our power grid, which has been built in the 1960s. They're already very outdated, already approaching their end of life. So we're seeing this kind of big congestions on both the supply side and also on the demand side. The whole industry from the IT side and also on the facility side, on the grid side, are all exploring different solutions. One big, very promising way that we're seeing could be a fast and easy to deploy right now is the battery energy storage system. We call it BESS. So there are two ways that we can use BESS to solve this problem. One is based on a pretty recent research from Duke University. It shared that we actually already have enough capacity in the power grid to power all the data centers. However, we just don't have the flexibility load. So the data suggests that even if we only provide 0.5% of flexibility load to the power grid, we can already unlock 100 gigawatts of a new load without any majority capacity expansion. On the other side, a lot of data centers that we're seeing already taking actions on building a lot of on-site power generation and on-site energy storage. One good example is Elon Musk XAI. They're building their Memphis data centers campus. If you look at the satellite image, they're already deploying a lot of Tesla Megapack batteries to support the local power demand. So these are all good examples and pioneer works showing how we can use this kind of plug and play batteries using lowest cost batteries and solar to provide a fast solution to solve the data center power demand, very burning demand right now that we have.
Catherine, I'll jump in with a question that I think may be in the minds of many in the audience here. Given the age and cost of the grid and the challenge building out more transmission distribution, and we're already seeing these batteries being deployed relatively cheaply. When will it be cheaper for batteries to be deployed for more time-based transmission than spatially uh, transmitted electrons via the grid?
This is a very frequently asked questions. So for many people who are not in the battery industry, might not know that actually right now batteries already become really cheap. If you go out right now to source the battery BESS, the battery energy storage system, the whole DC block of a LFP battery, lithium iron phosphate battery, right now you could be find them as lower cost as only $60 per kilowatt hour. Combined with the lowest cost of solar, it become a very cost competitive solution um, for the data centers. If you compare with building new transmission lines, you upgrading substation and sourcing transformers, which might have the lead time of up to 5 years. Yeah, so this is another point. It's sometimes not just about the cost, but also about the time, because
Mhm.
thinking about the whole new grid infrastructure with all the long lead time of all these critical components, which takes the overall 3 to 7 years to source and build. The fastest solution right now we're seeing a lot of data centers and hyperscalers are doing is actually using whatever is already exist and what where we can deploy super fast as a plug and play solution.
Yeah, very interesting. Thank you, Catherine.
And just as I said, these are some pictures that I took during I think 3 weeks 3 weeks ago during OCP, the Open Compute Project, and one from the GTC. So we're already seeing like as data centers approaching to megawatts per rack, we're seeing hyperscalers, all these tech giant, NVIDIA, OpenAI, they're calling for solutions and they're calling for support from the grid energy storage. Because we're seeing right now the data centers is approaching to 100 megawatts per site, or even growing to gigawatts per site. And then with all these huge AI clusters, huge AI factories, we're having terawatts of internet. Of interconnection queues for the power grid, which is it will take too long of time if we start to right now to build new transmission lines to accommodate those demands. And also these data centers, hyperscaler customer, they're willing to pay premium to get faster access to power and especially faster access to clean and firm power. And we are already seeing $100 billion already investing in this space, much more beyond the silicon level, but all more and more to every layer of the infrastructure, and also expanding to the grid level. Another challenge that we're seeing for the new AI data centers compared with traditional enterprise cloud is that the new AI training, the workload is causing a huge challenge. We're seeing a kind of this 100 megawatts of power swing and voltage spike, which is bringing big strike and pressure to the power grid. So that's why another reason why energy storage is needed, not only on the grid interface, but also we need more UPS BBU that is integrated to the facility and integrate to the rack.
Catherine, battery-based energy storage systems clearly seem to address the load fluctuations and a bunch of other issues that you just highlighted. My understanding is 90% of the global battery supply chain resides in China. And given the current geopolitical backdrop, how do you think the rest of the world is trying to decouple and become less reliant on China for its battery supply chain?
This is a very important point. Actually, my next slide, we're going to elaborate more. So we already know the pain is real and the need is urgent. However, our current battery energy storage solutions in the US is actually not ideal. For most of the battery energy storage solution that right now you're seeing deployed in the US is actually using NMC lithium-ion batteries, which are people manufacture for EVs. So when you use the wrong chemistry, when you use the wrong technology for the wrong market, boom, if you see the pictures here, this is what happened. So the picture here show the big fire event is actually already forced fire event in Moss Landing in California, which is caused by the NMC cell. So China is several years ahead of us. They're already progressing to use replacing LFP, lithium iron phosphate, as a new format for the as new chemistry selection for the energy storage solutions, which is a cheaper and safer and lasts much longer, which can contribute to a much lower levelized cost of energy storage. And we're even seeing that the development of the chemistry continue evolve to sodium, because compared with lithium-ion battery, NMC and LFP, sodium is critical mineral free. There's no lithium, no cobalt, no nickel, and very abundant. It's even much lower cost and even safer as energy storage solution. It's have a lower energy density, but it doesn't. It's no longer that matters that much, because this is used for the stationary storage instead of moving batteries from places to places. When we talk about safety, it is not just about the chemistry safety that we have to make it to safer, avoid catching fire, but more about anchor your question, the safe whether it is safe from the supply chain perspective. We all know that for lithium-ion battery, the supply chain is very dominant by China, from cell manufacturing to very upstream critical minerals, raw materials, key components are all 90% are made and dominated by China. So this is another reason that we are very interested in sodium-ion batteries and some alternative solutions, because sodium-ion battery, they are 1,000 times more abundant, and you can source them everywhere in the world. Actually, one of the best place you can source sodium is actually in the U.S. So in Wyoming, Trona, which is actually the largest soda ash reserve in the world, if you want to source for sodium-ion battery precursors. Yeah, so actually one company that we invested is called Peak Energy. Peak Energy, they develop a grid scale sodium ion battery energy storage system, and they are building a vertical integrated US supply chain for safer and lower cost and longer duration energy storage for the power grid and data centers. They have already built and deployed the world's first fully passive cooled grid scale energy storage system. I was there last week in Solar Tech site at their Denver to saw their pilot project. It's this really exciting project designed from cell to system by a group of former Tesla engineer and exec team. The company is about 2 years old and already progressing very fast with 100 million of contracts signed, and exciting project with leading utilities, IPPs, and hyperscalers.
All right, thanks so much, Catherine. We've now taken you through the journey of how electrons are created, how they're transported spatially and temporally. And now we'll discuss a little bit how end users are connected to this system and agree to long term offtake structures and ultimately procure electrons. So originally, when I saw this stat, I kind of rolled my eyes at it, but I think it gives a lot of good context that's, more understandable for the human inside of us. The near future nodes of GPU technology will pull about as much power as an American home. And so you can foresee that building tens of thousands to hundreds of thousands or millions of these GPUs within a data center is like building entirely new cities within our cities. We will eventually have to face the reality that data centers are now an integral part of our grid really woven into the fabric. Um, I think, while this could strike fears of power prices being bid up by eager customers, there is a promising angle to this as well. Recent Lawrence Berkeley National Lab work actually found that states with high load growth correlated with a decrease in energy prices. This is because more users can amortize the cost of fixed but maybe underutilized assets, which are very prevalent on the grid. Um, However, they did caveat that proper planning needs to be done for this positive effect to take hold. If not, they're already surfacing counterexamples where prices have been, bid up in certain regions. So this is a trend where we have to be very thoughtful. We're clearly at a crossroads where smart build out of these data centers and electrification in general could lower cost, but inflexible hasty rush build out could maybe hurt affordability for consumers. So, despite this crossroad for our power grid, I think it still makes sense for most data centers, and most data centers prefer to connect to the grid rather than completely decoupling from the grid and building their own on site power, as would be a very brute force solution to the problem. And we'll talk a little bit about why. Firstly, data centers require high reliability. I think we've all heard, these guys need on the order of 99.7 up to near 100% uptime, which can be very expensive and difficult without the grid that can get them near that without any redundancy. Although these data centers are relatively cost insensitive, getting to this level of redundancy where there might be spinning reserves, cold reserves, backup components sitting waiting to be installed can be very expensive, even for a data center with deep pockets. Furthermore, these data centers are huge. They incur massive capital costs. It was not that long ago, if you can see in the tiny graph in the bottom of the screen, a large data center just a few years ago was maybe 10, 30 megawatts. New projects are much, much larger. They're 100 plus megawatts up to a gigawatt. And I'd say finally, the reason the grid makes a lot of sense for these guys, um, while we feel like we don't know the future, they don't necessarily know the future all that much better than we do. They may want to ramp up or ramp down their interconnect in the future as compute becomes more efficient, or they want to scale up more compute on site. And if you build completely decoupled from the grid, it's not so easy to do that. You more have a fixed asset in place. And then, as Catherine covered, the reason this is all challenging is because our grid is super old. It's not easy to quickly study the feasibility of adding more power conditioning or switch gears or generation hardware on the same scale, on the same time scale that data centers need, rather. So, TDK Ventures has seen this problem, and we're tracking three major buckets of innovation that kind of sit amongst the same continuum of technologies to accelerate this speed to power. Firstly, in the top quadrant of the slide, you'll see what we call grid interface solutions. These solutions can facilitate the interaction of large loads like data centers with the grid to get them faster interconnect or could potentially tap underutilized resources. One really exciting tech here is the coordination of compute to reduce congestion on the grid. These are generally software native solutions that can take active control to shift workloads across time and location, maybe to respond to demand and help the grid ultimately. Other solutions may be more primarily focused on communication between the utility and data center operators, which currently is fairly archaic. Often we hear anecdotes about communication through phone calls. You can really update these demand response tools with real time visibility, controls, maybe even automated demand response so that this phone call can be eliminated. Finally, in this sector, some startups can help to accelerate interconnect approvals or identify capacity with better grid modeling and simulation, and potentially propose more efficient routing options for electricity. Now, moving
Josh,
forward.
sorry, go
Yeah,
ahead.
no, please go ahead.
Yeah, I just had a quick question on this slide. What role do local governments have in power procurement for data centers?
Hmm. Yeah, so I guess local governments are most definitely major stakeholders in the siting of data centers. I think to kick off that answer with some anecdata that we've collected, we hear manufacturers and businesses that share a grid with the data center not only are worried about their prices being bid up, which is very real for electricity consumption, but are also seeing their power quality worsen. So the local businesses are very worried about blackouts and huge voltage swings based on um, these batched AI workloads. I would say, secondly, we've seen data centers, being shut down across the country many times due to concerns in water prices, where data centers often request up to a million gallons of water access per day. And in certain regions, that can be a very big ask. So, um, rightfully so, I think local governments are a little bit skeptical of this build out. But I think nodding to what we showed before, local utilities are actually incentivized to get these data centers on the grid. They can help to amortize cost and decrease rates for all consumers. But there's also political pressure, right? Where, bringing in a large tech company that might operate a data center can be very promising for job growth in certain regions. And so, look, there are two sides to the coin, but ultimately, the local government has a very big role to play in this. Yes, Encore. So, thank you for the question. And I think that does bleed in nicely to the next kind of topic of innovation that we see at the bottom of the screen, which we call powered land development. These are startups that are bringing in, full fledged from dirt to power development of sites with dedicated generation that might be wind, solar, batteries, gas, whatever it might be, that is sized perfectly to the compute load that they will eventually agree to a long term offtake with. They could also lease the land to data centers. Developers here will prioritize whatever they can to deploy most quickly and most reliably, and they'll optimize for speed, uptime, and cost. I think the real key advantage of what we're seeing here now is this bespoke development allows for the co-design of power as well as the facility systems on the data center from day one. This includes cooling, heat reuse, auxiliary systems, and it can result in higher overall efficiency of the data center. And then finally, the last bucket we see in innovation that we're very interested in, we have called it on-site power solutions. This comes in at a slightly smaller, more targeted scale than full powered land development. Startups here might bring temporary power solutions like mobile batteries or maybe even operational microgrid software to ensure that microgrids are operating at their peak. And ultimately, these solutions have to balance load and storage and different sources while meeting the agreed upon service level agreements of the data center. And we see solutions here can either turn into long-term assets that might work in harmony with the grid and help data centers to curtail when they need to, or they could be primary power for a short time, kind of like a genset, and bridge the gap between when IT infrastructure can be developed and grid interconnect becomes available. I think the industry has come to know this as bridge to power. So I think one additional mega trend that we're seeing here that we would really like to highlight is load flexibility. Due to the need for power access, data centers are now willing to agree to demand response events and even flex their interconnect. They could soak up all available grid capacity when it's there and come with their own strategy to supply power or respond to demand when they need to. Traditionally, data centers have been cited for the very worst time of the year on the very hottest summer day with no available grid capacity whatsoever. This period might only be a few hours, maybe even a few minutes per day. And I think on the slide, this firm power offtake is denoted by the white dotted line that is significantly below the maximum power that a data center in this example would want. Flexible data centers, on the other hand, as Catherine pointed out, could enable up to 98 gigawatts, near 100 gigawatts of new industrial load using existing and underutilized infrastructure already on the grid. And the example here, the data center uses pretty much as much power, denoted in blue bar graph, as available, and then bridges the gap to the power that they actually need at any given time with their own off grid power, shown in yellow there. Means for supplying this off grid power aren't necessarily just generation, though they could be on site generation and storage. You could also coordinate local grid assets and build a VPP to respond to demand response events. You could even curtail or flex your auxiliary systems like HVAC on site, or potentially you can even shift the compute load. You can queue up jobs that don't need to run right away. You can curtail the ramp rate of GPUs in the data center, or you can shift them spatially to new data centers. We'd like to really quickly
Great. One
highlight.
one question, Josh. Can you
Yeah,
yeah. So one question for you. So it's glad to see there's different means for data centers to manage the load flexibility, but why haven't data centers been willing to participate in this kind of demand response in the past?
yeah, okay. Thank you for asking that. I think a little bit of context here is needed because you see this and you think it's, pretty obvious. Like, why aren't we already doing this? Um, the the CEO of a company innovating in the space, Emerald AI, said it really well. Um, Basically, the necessity is the mother of innovation here, where in the past we haven't had the same need for getting data centers connected as quickly as now. There are hundreds of gigawatts sitting in queue, and without some kind of compromise, this build out won't happen. And they're really desperate to make it happen, right? Because I think estimates we've seen for every year that they don't get access to power is something like $7 billion to $12 billion per gigawatt of data center year. Not on the grid. So they're really willing to compromise. But what has kind of really logistically prevented this in the past is the fact that data centers sit in this sort of not so friendly strategic sandwich where on one side they have customers that expect their service level agreements to be met where they require, as we pointed out, 99.9x% uptime, and on the other side of that agreement is a power provider who has agreed to ship power to the data center long term, and if they didn't offtake as much power as needed, they would be punished fairly severely for failing to meet their agreed offtake obligation. Um, and so in the past, right, there's been no reason to be flexible, and no real motivation to break these contracts. But now moving forward, it makes a little bit more sense for all parties to come together and say we have a shared goal of getting data centers on the grid more quickly. So how can we kind of agree to better offtake structures? And this is what is really surfacing. So thanks, Catherine, for the good question. I think before I hand it over to Ankur, I want to highlight one of our portfolio companies, Ampere Sand. They're developing novel solid state transformer technology. Solid state transformers are on the critical path for data centers and electrification in general, as as solid state transformers provide more flexibility and capabilities than traditional transformer tech. They can accept and convert a much wider range of electrical source and load conditions. We were proud to back Ampere Sand at their seed stage very early on in the company's life cycle. And Ampere Sand, as an early mover in the space, already has a product ready for deployment right now, which we are excited to watch them demonstrate at the port of Singapore, where they can showcase solid state transformers have many advantages across speed to deployment, efficiency, and power density. And after their demonstration at the port of Singapore, they do eventually plan to move towards data centers and helping get these guys power more expediently.
Thanks,
On
Josh.
the
Yep. As the global compute demand grows exponentially, the next frontier isn't just faster chips, it's smarter, energy conscious computing. Each electron must be optimized, and we are seeing compute and connectivity innovations in how electrons are consumed. Let's talk more about these innovations. First, next generation compute architectures. We're moving beyond one size fits all CPUs and GPUs. Heterogeneous systems blend CPUs, GPUs, FPGAs, and custom accelerators, choosing the right engine for the right workload to deliver dramatically better performance per joule. And taking inspiration from biology, neuromorphic chips mimic the brain's synaptic efficiency, enabling AI at the edge with almost no energy overhead. Even quantum inspired approaches are helping solve previously impossible optimization challenges using a fraction of the power. Our portfolio company, Grok's purpose-built AI accelerator reduces latency, improves throughput, and enhances energy efficiency compared to general-purpose GPUs. While another portfolio company, Sagensys compute offering, is rethinking the memory compute boundary and enabling leaps in energy efficiency.
Ankur, before I jump to the next slide here, I do have a question. This all sounds very nice, but do you see that chip vendors really, have power top of mind when they're developing, next gen technologies?
Absolutely. Chip makers today cannot design in isolation. They must consider not just how fast a processor goes, but how many electrons it draws and how much heat it dumps. And the data center operators using those chips are increasingly constrained not by compute, but by power and cooling infrastructure. I think one estimate is the compute chips themselves represent about 40% of data center electricity consumption, with cooling and infrastructure representing much of the rest. So energy consumption has moved from being a secondary metric to a first order design parameter. Now let's talk about the next innovation, which is in photonic computing, that is using light instead of electrons to reduce consumption of electrons. Photonic chips, neural networks, and optical interconnects reduce resistive losses, cut heat generation, and move data at terabit speeds. That means AI workloads and data center operations can run cooler, cleaner, and far more efficiently. In this regard, our portfolio company Nubis pioneered high performance, ultra compact, low power optical interconnect solutions and was recently acquired by Ciena for its product leadership. We've made another investment recently in the space of co-packaged optics that has not been disclosed yet. We're also seeing major innovation in cooling and materials like immersion cooling and advanced thermal interfaces that reduce cooling energy requirements by up to 70%, unlocking sustainable high-density compute. Our portfolio company, Novolink's technology, leverages unique nanocomposite and nanomechanical design innovations originally incubated at the Carnegie Mellon University to provide advanced thermal management solutions. And finally, edge intelligence brings processing closer to where data is created or inference is needed, reducing transmission losses while enabling real-time action. One of our recent investments, undisclosed so far, is focused on energy-efficient AI processing at the edge. They have adopted a unique software-first, hardware-software co-design approach to design AI chips optimized for low-power edge inference across various edge and IoT applications.
One question, Anku. So in all these different type of chip design, what are the trade-offs in optimizing for power consumption?
Yeah, Catherine, I think that's a multi-billion dollar problem. So when optimizing for power consumption, engineers are balancing a complex set of performance, cost, latency, and scalability trade-offs across every layer of the stack. Lowering the power consumption often means reducing voltage, frequency, or active cores, which can diminish peak throughput or latency. Also, achieving high efficiency often requires um, custom silicon, advanced packaging, or exotic materials, which can drive up the cost and complexity. Every watt saved has a cost in performance, complexity, or flexibility. The challenge is no longer about choosing between power and performance, but optimizing across them.
Thank you.
So, in summary, as AI scales, we are entering a new economic reality. We used to think about data centers in terms of compute density. Today, the first question isn't how many GPUs can we rack? It's how much power can we get? So energy must become a first-class design metric right alongside price, performance, and programmability, or what I like to call the 4 Ps of data center design now. Because without energy, none of this intelligence happens. This is where entrepreneurs have a massive opportunity. Energy efficiency is not just a sustainability goal, it's a competitive differentiator, directly shaping total cost of ownership, deployment speed, and carbon footprint. And the solution isn't just in one layer, it's in a holistic system design, from new compute architectures and advanced cooling to software-defined energy orchestration and renewable energy integration. Everything must work together to optimize use of each electron. The future of data center is not just powerful, it's energy aware, dynamically adapting to workload needs and the realities of the power grid. So, to all the founders here, if you can help build data centers that think about energy as intelligently as they think about compute, you're building the future of AI. And we want to partner with you. Thank you. And with that, we can take some questions or comments from the audience.
All right, Catherine Onker, thank you guys so much for the good discussion. And I do see we have a number of questions from the audience already coming in. Um, I think I will start with a really top of mind question from Mohit. Let me see how I can bring this up. He asked, there are a number of Onker, is that showing for you?
Actually, the question disappeared just now. Maybe it was answered.
It did just disappear. But he
Yeah.
he asked, there are a number of startups operating in the power capping space for GPUs, um, and wanted to know how promising they are and if they are very dependent on the OEM hardware. And I think what I would say is they are, for the most part, quite early on. They're really at the pilot stage, but from our understanding, they've shown that by capping the the ramp rate of GPUs, they can meet the load response demands that their pilot utilities have requested of them mostly. And for some of these emerging companies, they've already touched the customer to some extent where the customer has seen really very minimal or no decline in their performance of the models. However, I think the question that is really pertinent is, are the large hyperscalers going to go and try and build these solutions themselves? And if so, where will the most value from a third party come from? Um, and then to the second part of that question, um, which was how dependent on the OEMs are they? I think in general, in the data center, we've seen verticalization. Maybe Ankur knows more about this than I do, but the large couple names like NVIDIA tend to not only take control of the end compute, but more into the power stack and farther into designing the topology within a data center. So, yes, the answer is it is very dependent on on these compute OEMs. However, they generally come with an API that is very accessible for these startups to plug right into, as is, necessary for day-to-day compute operations already. So while they have an outsized control of the data center, um, it's not going to be as big of a leap for some of these kind of power capping companies that are popping up. So thank you for the good question.
I think there's another aspect to Mohit's question around model pruning to maximize compute per watt.
Mhm.
Absolutely, we are seeing software approaches that distill, prune, and make the large language models or deep learning models smaller to be able to run on edge devices. In fact, the company that we recently invested in the edge intelligence space also has a technology in software to make the LLM and deep learning models tinier and be able to run in less than 30 watts of power. So absolutely, along with hardware innovations, we're seeing software innovations to make complex models tinier and less power intensive when run on edge devices.
Great. Now, I think we have time to field one more question. Um, Catherine, did you see anything from your end that you wanted to address?
I think all good. I think you guys did really good answers.
Great.
I think
Janet?
there was a request for emails. We'll absolutely be sharing our emails. So I don't think we'll be able to address all the questions in the next 5 minutes, but please do reach out with ideas, with questions, and anything else on this presentation.
Great. I think, Catherine, maybe one question for you that would be great to address before we wrap up here. Um,
Sure.
Bethany asked, how do we feel about thermal energy storage as a way to, transmit electrons temporally, spatially? Um,
Sure.
what are your
So
views there?
yeah, we evaluated several thermal storage technologies and innovations. Um, we like them. It's a one option. However, the biggest concern that we have, or our investment thesis built it, is the round trip efficiency is not high enough. So especially for applications that you're losing power cycles after cycles, compared with battery energy storage, which you got all the hardware costs, continue riding the cost curve of getting cheaper and cheaper. You see in the past 10 years, battery costs already reduced by 90% on the cost. And thermal energy storage is first we're not seeing the hardware cost continue riding the cost curve, and we're not seeing an attractive round trip efficiency unless your application for the thermal storage is the application of heat. So you're using some of the industrial heat, depending on low grade or high grade. For those conversions, it makes sense, but we don't think it makes sense. You convert heat to electricity and then convert it them back. So it's just too low of round trip efficiency compared with other storage solutions.
Okay, great. Thank you, Catherine. I think with that, we're pretty much at the end of our time here. So we want to thank everyone for the very good questions. As Ankur said, we'll share our emails, so we would love to continue the conversation. We appreciate you for sticking with us through this presentation and hope we can work together in the future. But thank you all.
Thank you, everyone.
Everyone.